Hello there, and welcome to these next three sections. These are sections 9.4, 9.5, and 9.6, and they cover what are known as convergence tests for series. Okay, we're going to kick things off by looking at the first problem on the worksheet, which is actually a nice recap of a number of things we looked at towards the end of section 9.3. And so to begin, recall what we referred to as the test for divergence. Okay, there we saw that if a sequence a sub n does not approach 0, as n approaches infinity, then it must be the case that the series of a sub n diverges. Okay, now what we call the contrapositive of this conditional statement, that's what you see directly below. This is also true. This says that if we know that the series of a sub n converges, then it must be the case that the sequence a sub n approaches 0 as n approaches infinity. All right, so now let's look at part A. It says, true or false, if a sub n approaches 0 as n approaches infinity, then the series of a sub n must converge. Okay, now we have to be really careful. Here in part A, we're assuming that a sub n approaches 0. And notice in neither one of these statements above is the assumption that a sub n approaches 0. Now, a sub n approaching 0 is the conclusion of the second statement, but because it's not an assumption of either one of these statements, these two statements in fact say nothing about whether or not what we see in part A is true or false. Okay, so here we're going to go back to an example we've already seen, and we're going to go back to the harmonic series. Okay, the harmonic series illustrates why the statement is in fact false. Here with the harmonic series, a sub n is 1 over n. It approaches 0 as n approaches infinity, but the series of 1 over n, as n goes from 1 to infinity, we actually proved diverges. Okay, so we have to be, again, just very, very careful here. If all we know is that a sub n goes to 0, it may not be the case that the series of a sub n converges, right? It is possible for the associated series to actually diverge, as the harmonic series illustrates. All right, so now let's move on to part B. It says, suppose that the series of a sub n is equal to 2. Find the limits of the sequences a sub n and s sub n, where s sub n is the nth partial sum of the series. All right. Now, since we're told that the series of a sub n is equal to 2, then in particular, this really is saying that this series is convergent, right? It's convergent and has a sum that's equal to 2. So from the second statement up above, since we know the series converges, then it must be the case that a sub n approaches 0 as n approaches infinity. So that is our first limit. All right, now what about the limit of the partial sums, the s sub n? Well, for that, just go back to the definition of a series. Okay, so by definition, this series of a sub n is equal to the limit of the partial sum s sub n as n approaches infinity. So here we get that the limit of the partial sums is equal to the series of a sub n, and we're told in the problem that is equal to 2. All right, very good. So now let's go ahead and look at part C. It says, for each part below, give an example of a series that satisfies the stated conditions. So in part 1, we want a sub n to go to 0 and the series of a sub n to converge. And then in the second part, we want a sub n to go to 0, and now the series of a sub n needs to diverge. All right, so make a little space here first, and then let's look at part 1. So for part 1, we really can choose any series that we know to converge, because if we know the series converges, then it has to be the case that a sub n goes to 0. So in particular, I'll go ahead and use our very, very first example of a series. That was where we looked at Zeno's paradox. Okay, so there a sub n was equal to 1 over 2 to the n, and this goes to 0 as n approaches infinity. And we proved that this series, right, summed to 1, right? And another way to say that this series converges is just to say, hey, it's a geometric series with common ratio r equal to 1/2, right? But however you want to argue that, right, we know that this series converges. All right, so that satisfies the conditions for part 1. For part 2, we want a sub n to go to 0 and the series of a sub n diverge? Well, we just looked at an example, right? This is the harmonic series. Here, a sub n is 1 over n. That goes to 0 as n approaches infinity. But the series of 1 over n, right, that diverges. Okay, so the big takeaway from part C is that if all you know is that a sub n goes to 0, then it could be the case that the associated series of a sub n converges, or maybe it diverges, right? And these two examples illustrate both scenarios, okay? So you'd need to do more work, right, to uncover whether or not the associated series converges or diverges. All right, cool. So now for part D, it says, suppose that the series of a sub n, where here n goes from 1 to infinity, is convergent. What can you say about the series of a sub n, where now n is going from 10 to infinity? Well, this is related to what we're going to call the tail end property of series. And here's what the tail end property says. It says that if we know that the series of a sub n, where n goes from 1 to infinity, so this is just a1 plus a2 plus a3, so on and so forth, if we know this series converges, then the series where we start the index n at some number capital N, so in other words, a sub capital N plus a sub capital N plus 1, plus so on and so forth, this series also will converge. And that's true of any starting index capital N that's greater than or equal to 1. Okay, so in part D, the capital N there is 10. So the big takeaway there is that since in part D we're assuming the sum from 1 to infinity converges, the conclusion then is that the sum from 10 to infinity also will converge. Okay, now let's go ahead and prove this tail end property and then summarize. So proof is actually not too bad. So here I start by just writing out the series starting at 1. So this is a1 plus a2 plus blah, 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 up until we get to a sub n minus 1, then plus a sub n, plus a sub n plus 1. And I'm just including these terms there just to make the next couple of steps clear. So again, in part D, capital N there is 10. So this would be the sum from a1 up to a9, then a10, a11, so on and so forth. All right, so now I have on the left what I'll call the full series, where we're summing from 1 to infinity. And then I'm going to call these first n minus 1 terms the front end of the series. And then the sum from a sub n on, I'm going to call that the tail end of the series. And what the tail end property for series says is that if the full series converges, then this tail end of the series must also converge. And the reason why is, well, as follows, right? So the tail end, this thing right here, see if I subtract the front end from both sides of this equation, we see that the tail end is just equal to the full series minus this front end. And if we know that the full series converges, and this front end, well, this thing is just a finite sum, right? So again, like if capital N was, say, 10, this would just be the first 9 terms added together. So this is just going to give us some number. And the full series being convergent, right, this will have some finite sum, right? Say, let's just illustrate, like, let's say this series converges to 2. And then this front end, right, this has a sum that's equal to, say, 0.3. So this would be just 2 minus 0.3, which would give us 1.7, right? The big takeaway, though, is that this converging and this just being some finite sum tells us then that this tail end series must itself converge. That's the big takeaway. So if this converges to some number, here we're just taking away some finite sum, right? Some number, then this thing right here must also converge. And so that is our proof. All right, so then, again, to summarize, for part D, if the sum from 1 to infinity converges, then the sum from 10 to infinity converges as well. All right, well, that's a good place to stop. I will see you in the next video. Thanks.